Let's solve the first one. Let R be a relation which contains 6 attributes, namely A, B, C, D, E, F, be a relation schema with the following dependencies like C determines F, E determines A, EC determines D, A determines B are the FDs. Which one of the following is a key for the R? Answer is EC. Why EC? Right? If you take EC, EC is definitely necessary attribute because they are not on the right side. So if you take any kind of a candidate key, definitely there has to compulsory EC. Right? So the necessary attributes are here E and C, and as there are only the 2 level attributes are there, so I can say directly option is B. Or what you can do, you can just take one by one and you can get the entire relation, then that will be the candidate key. So option B is the correct answer for this one. What about the second one? RBA relation, which of the following does not have lossless dependency preserving BCNF decomposition? Means what you have to do now, for the given relation, which one of the following is the correct one in the BCNF? So what you have to do? You have to make the relation up to BCNF, right? If you take the relation R of ABCD, and let's try to do it with the first one, right? If you take the first one with R as a relation, R relation, and is it in 2NF? Is this one is in 2NF? What is the candidate key here? In R relation, candidate key is A, right? As candidate key is A, candidate key is A, is there any chance of getting partial functional dependencies? No, as there is only one attribute, there is no chance of getting partial functional dependencies. So obviously there is no partial functional dependency. So it is in 2NF. It is in 2NF. What about 3NF? 3NF, it should be free from partial functional dependency. But is it partial functional dependencies? Is it transitive functional dependencies are there? Yes, right? So means what you have to do again, you have to decompose this relation into 2 relations. One is BCD. So you have to find out the B closure. B closure is BCD, and the remaining thing you have to write as one more table, that is AB. Right? Now, what might be the FDs possible? B determines CD and A determines B. A determines B, right? So this is what a kind of 3NF now. What about the BCNF? Is it in BCNF? Yes, it is already in BCNF because the formula defining LHS should be a kind of a candidate key. That's it, right? So both relations contains the LHS a candidate key. I can say that it is in BCNF. Now, B is not. Why? B is a candidate key. After splitting the table, we got the relation as BCD. In BCD, what is the candidate key? B, right? On the left hand side is a key, so I can say that it is in, it is following the BCNF property, right? So it is now in BCNF. After BCNF, which of the following does not follow in the lossless join as well as dependency preserving? Obviously, you know, right? Lossless join is going to be satisfied definitely. What about the dependency preserving now? So in the main table, A determines B is there. In the division table, A determines B is there. In the main table, B determines CD is there. In the small table also, B determines CD is there. So dependency is preserving. So option A is valid one. So take out the option B. In option B, if you decompose, what might be the candidate key? A is the candidate key. A only determines all the things. That's why A is the candidate key. As there is only one attribute in the candidate key, I can defaultly say that it is in 2NF. What about 3NF? 3NF is not going to follow. At what level? B determines C and C determines C. So it is validating at 2 levels. What you have to do? You have to find out the B closure. You will get BCD. You will get BCD. And what about another one? AB. Right? Now, between these two, what is the common one? B is the common one. Now, this relation is in 3NF. Why this relation is in 3NF? If I say B determines C, C determines D, A determines B, is it in 3NF? No. Why again? Here the candidate key is B. So B determines C is okay. What about C determines D? Again relation between the two non-key attributes. So it is transitive functional dependency. So what you have to do? Again split this table into multiple tables. So you have to split as BC, CD, and this relation as usual AB. Right? Now try to check. This is B determines C. This is C determines D. This is A determines B. Now definitely it is going to be 3N. And as every LHS is a kind of a candidate key, it is in BCNF. Right? We decompose up to BCNF. Now we have to check for whether these are preserved or not. Is A determines B is preserved? Yes, A determines B is preserved. B determines C, preserved. C determines D, preserved. So option B is also valid one. So meaning that lossless join is satisfying as well as dependency preserving also satisfying. But they are specifically asking here does not apply. So what about third option? Third option is if you take what you can do. So what is the candidate key here? AB is the candidate key. Is there any single level attributes are possible for the candidate key? A is not possible, B is not possible, C. From C I can get C, A, D, but I cannot able to get B. Because if you observe the necessary attributes contains the minimum B. If you observe this option C, on the right hand side, necessary attribute is B. So B has to be compulsory. So B with anything we have to add, right? So B with if I add A, are you going to get the candidate key? Yes. So I can say that AB is the candidate key. Once AB is the candidate key, now can I say that any partial functional dependency is there? No partial functional dependency is there because either A or B independently defining one functional dependency. So it is in directly in 2NF. Is it for B? Can I add C? If I add C, CB is a candidate key. Good. What about DC? DB. DB is not a candidate key, right? So we find 2 level. What about a 3 level? 3 level, you have to compulsory include B. You have to include 3 level means what? 3 levels you required, right? First one, second one, and third one is compulsory B. What about the second one? Second one, I can include D. I can include D. Okay na? If I include anything, what will happen? Super key out. So there are no 3 level candidate keys are possible. Okay na? So the candidate keys possible here are A, B, and C. A, B, and C, B. Now you can answer. Is it in 2NF? Is it in 2NF? So AB determines C is okay. What about C determines AD? C determines AD. Now C is a part, right? C is a prime attribute. A is a prime attribute, but D is a non-prime attribute. So definitely it is not in 2NF. Definitely it is not in 2NF. So when it is not in 2NF, you have to make it into 2NF. Right? So how can you make it into 2NF? C, AD is one relation. What about the another one? Remaining remaining A, C. Because C is the candidate key, right? See, 1 minute. Here you can check. I am trying to write the new table for C determines AD. C determines AD, right? When I am checking for C determines AD, I am going to create the new table called CAD. That is okay. So if I cancel out, okay, A, D, the remaining thing will be BC. Is it okay now? BC. So this is my new relation. So if I got the new relation, you have C determines AD and B determines C, or it might be C determines B. It might be C determines B, right? So try to check which one is correct. What is the B closure? B closure is B, so B determines C is not possible. What about C closure? So which is not possible? So anything is not possible. Okay. So in 2NF, we got the one FD as C determines AD. C determines AD, right? So now it is in 2NF. What about the 3NF? If you would like to say it is in 3NF, what you have to do? So it should be free from transitive functional dependency. So what might be the FDs possible here? See, find out B closure first here. What is B closure? B closure is B, right? And C closure is CAD, right? And any other things are possible? No. There are no other things are possible. So there are no functional dependencies are possible. So with this, I can say that directly, I can stop here because these functional dependencies may not be possible in further also. So that's the reason option C is the correct answer directly. Or if you want, you can just cross check with this one, you will get the answer. Right? Why fourth one is directly answerable? There is only one FD. Only one FD. That too, A is a kind of a candidate key which is already in BCNF. So I can directly say that lossless is happening as well as dependency preserving also satisfying. So option C is the wrong one. సో ఒకసారి మీరు మళ్ళీ ప్రాక్టీస్ చేయండి సో దట్ యూ కెన్ గెట్ ఐడియా. ఓకేనా? ఇంకా క్లారిటీ రాకపోతే ఒకసారి నేను చెప్తాను కావాలంటే. ఓకే, లెట్స్ సీ ద థర్డ్ వన్. Which one of the following statements about normal forms is false? BCNF is stricter than 3NF. Lossless, dependency preserving decomposition into 3NF is always possible. Lossless, dependency preserving decomposition into BCNF is always possible. Any relation with two attributes is in BCNF. So we can go with the elimination option, right? So is BCNF is stricter than 3NF? Yes. So which is correct statement? BCNF is stricter than 3NF. And if I say that any relation with two attributes is in BCNF, yes. What about the option B or C? With our examples, I can directly say that option C, lossless dependency preserving decomposition to BCNF is always possible. Is it the false or true statement? False statement, right? Our last example clearly shows that FD preserving is not done. So I can say that option C is the correct answer for the given question. Meaning that option C is the false one. And this is also a true one. Next one. If a table having fields like F1, F2, F3, F4 and F5, the following functional dependencies, F1 determines F3, F2 determines F4, F1, F2 determines F5. In terms of normalization, this table is in. So for this solution, what you have to do? You have to calculate the first candidate keys, right? What might be the candidate keys? So go with the necessary attributes. Necessary attributes are F1 and F2, right? So if F1, F2 might be a candidate key, try to find out it. F1, F2, F1 determines F3, F2 determines F4, F1, F2 determines F5. So candidate key here is F1, F2. If candidate key is F1, F2, what might be this functional dependency? F1 determines F3? Partial. When there is a partial functional dependency, what we can say? Which is in 1NF but not in 2NF. So obviously option A is the correct answer. Next one. Which of the following is true? Every relation is in 3NF is also in BCNF. Is it true? No. So if it is true, why they implemented the new one, BCNF? Right? So that's the reason this statement is false. This statement is false, right? Next, a relation R is in 3NF if every non-prime attribute of R is fully functionally dependent on every key of R. Means what they are saying, if I say that a relation R is in 3NF, every non-prime attribute of R is fully functionally dependent on every key of R, meaning that LHS is a key, RHS is a kind of non-prime attribute. Is it the correct one? Okay, let us come to this point later part. Right? Try to check the third point. Every relation in BCNF is also in 3NF. Obviously, right? So, what might we think, like if I am saying that something is in BCNF, it has to minimum criteria is 3NF. So, everything which is in BCNF has to be 3NF. So, option C is the correct answer. Option D, no relation can be in both BCNF and 3NF. Obviously false, right? We have seen many examples where if it is 3NF, it will be again BCNF also. But here they are saying that both are not same, right? So it is false. What might be the option B? Right? They have given clearly directly definition, but the definition includes what? Another case. What is another case? Left side can be anything, right side can be prime attribute. But if they have included this point also, option B is also important, correct one. But as they have skipped only this one, you have to make this also a false statement. Okay, now fine. Next one, for a database relation R of ABCD, where the domains A, B, C, D include only atomic values, only the following functional dependencies on those that can be inferred from the whole A determines C, B determines D, the relation is in. So, meaning that what might be the maximum normal form, it is following. So, first you have to find what? Candidate key. What might be the candidate key? In the RHS side, AB is not there. So, minimum AB should be the candidate. AB have to be part of the candidate key. If you find out the AB closer, definitely you are going to get ABCD. So, AB is the candidate key. Right? Once it is candidate key, a part of it is already determining something. So, I can say that partial functional dependencies are there. Once partial functional dependencies are there, it is in 1NF but not in the 2NF. Okay, now. Next one. Right? So, solve this one. I think this one will be the 7th one, right? So, given the following relation instance, which are the following functional dependencies are satisfied by the instance? So we have to check it, right? All options you have to check, right? So is xy determines z, right? Xy is completely unique, which can determine z. What about z determines y? False, right? Z determines y is false for this case. 2 determines 4 as well as 2. So which option A is wrong? What about option B? Yz determines x. Yz is unique. Unique, there is no problem. What about y determines z? Again, y determines z is unique again. So option B is true one, right? So what about option C? Yz determines x. Okay, yz is unique. What about x determines z? No, x is same, z will be modified. So I think it is very clear for you. Right? Option B is the correct one. Next, they have given a relation R which was decomposed using a set of functional dependencies called F, and relation S decomposed using another set of dependencies called G. One of the decomposition is definitely a BCNF and other decomposition is definitely a 3NF, but it is not known which is which. Means that they have clearly given a relation R with the help of some set of FDs. they have decomposed into a set of relations like R1, R2 and R3, assume that, right? And there is one more kind of relation S is there, they have decomposed into S1, S2 and S3 with the help of some set of functional dependencies. Now they are saying that either of them, one will be BCNF, another one will be 3NF, one will be 3NF, another will be BCNF definitely, but they don't know exactly which one is which. We have to define which one is which one. So for that, what they are asking now, to make a guaranteed identification, which one is BCNF, which one is 3NF, which one of the following tests should be used on the decompositions. Means that what kind of test we can able to do on these relations, so that we can able to define which is which one. Can I apply the property of decomposition preservation, so that can I say that it is in some kind of thing? No. Why no? Up to 3NF, definitely it is going to be lossless decomposition as well as dependency preserving. There is no problem. But if you go for BCNF, in BCNF, the decomposition can be dependency preserved sometimes, and as per our last example, dependency may not be preserved, right? So we cannot able to guarantee, meaning that we have two possibilities are there. So with the help of dependency preserving property, we cannot directly say that it is BCNF or 3NF. Obviously 3NF is there, but we cannot able to guarantee that whether it is BCNF or not. So option A is wrong. What about lossless join? Again we can get ambiguity, because 3NF having lossless join, BCNF having lossless join. So with the help of option B also we cannot able to define. What about BCNF definition? Obviously BCNF definition we can able to define. But what about the 3NF definition? May not be, may or may not be. Why may or may not be? Because it is having the combination of R case, right? If at least one is followed, then other might be something, right? So that's the reason. With the help of 3NF also we cannot able to define, but with the help of only BCNF definition, we can say which one is BCNF, which one is 3NF. Next one, consider the relation R on which of the following functional dependencies holds. What are the candidate keys? So with the help of options we can directly go, right? Or what you can do, go with the necessary attributes. What might be the necessary attributes? A is there, B is there, C is there, D is there. So A, B, C, D is there, but EH are not there. So meaning that if I am saying that something is a candidate key, definitely it has to have EH, right? So if EH is there, option A and option B are going to be eliminated. Option C also eliminated. Option C eliminated. Why? It is BCH, not BH. So option. So directly we can say that option D is the correct answer. So if you want, you can just cross check. Next one. A relation employee DT1 is defined with the attribute EMP code bracket unique nature. Unique name, street, city, state and pin code. For any pin code, there is only one city and state. Also, for any given street, city and state, there is just one pin code. One pin code. In normalization terms, EMPTD1 is in what relation? Can you say? What might be the answer for this? Right? So here you have to formulate. What you have to formulate? Employee code is unique. Employee code is unique. Once the employee code is unique, can I say that it's a candidate key? Once it's a candidate key, can I directly say it is in 2NF? A single attribute is a candidate attribute is there. That attribute itself contains only one attribute. Can I say that it is in 2NF? Obviously it is in 2NF. What might be the 3NF? For 3NF, any given conditions are there. See, observe, for any pin code, there is only one city and state. How can we write that? Pin code determines city and state. Also, for any given street, city, state, which can determines pin code, right? These are the two functional dependencies which you know, right? Is there any transitive functional dependency? Is there? By directly observing, there is a transitive functional dependency. Once there is a transitive functional dependency, can I say it is in 3NF? Why I am saying that these two are transitive functional dependencies? Because candidate key is kind of employee code. Employee code is the candidate key, and all the remaining things are non-candidate keys, non-prime attribute, right? As there is a relation between non-prime attributes, definitely they are in transitive functional dependency. So as it is not free from the transitive functional dependencies, I can say that it is not in 3NF. So option is B. It is in 2NF and hence also in 1NF. Next one, in a schema with attributes A, B, C, D and E, following set of functional dependencies are given. Right? They have given some set of functional dependencies. Which are the following functional dependencies not implemented by the above set? Meaning that we have to apply some set of rules and we have to get the remaining things. So what is the simple solution for this? They have given some set of functional dependencies and they have given some other additional functional dependencies. We have to define whether they are derived from the given set of functional dependencies or not. Simple thing is we can able to find out closure. So first one is CD determines AC. If I find out CD closure is what? CD, E. From E I can get A. So I can say that AC is possible. So option A is not the one. What about BD closure? BD. That's it, right? Meaning that it cannot able to determine CD. So option B is the correct answer. Right? Which one of the following functional dependency not implied from the above given functional dependency? So option B is the correct answer. Okay, now next one, let R be the relation schema with the following functional dependencies. So they have given the functional dependencies like this: the decomposition of R into multiple relations. One is AB is one relation, BC is one relation, BD is another relation. So they are asking that whether they are lossless or dependency or both are not following. That is what they have given. So what you can do? Can we calculate whether they are lossy or lossless? First, is it lossy or lossless? What you have to do? First you have to combine, right? When you combine R1 with R2, what is the common one? B is the common one. When B is the common one, what is the closure of B? BC. It is getting at least one relation. So I can say that I can combine easily. There is no problem. Right? Once we combine, you are going to get ABC. Now this one I am going to combine it with R3. What is the common one? B. If I find out the B closure again, B, C, from C I can get D. I can get D, right? So meaning that indirectly, am I getting another relation R3 or not? So meaning that B is a candidate key here. When you are going to combine with respect to candidate key, definitely it is going to be lossless. So the given decomposition is lossless decomposition. Fine, right? Means we can eliminate simply option C and option D. What about option E and option B? You have to check for functional dependency. Functional dependency preserving means what? You have to check whether these dependencies are preserved over these decompositions or not. Right? So for R1, what might be the FDs possible? What is A closure? A closure is AB, means A determines B. What about B closure? B, C, D you will get, but those are not in our relation, so only one FD is possible, that is A determines B. Okay. Next, What about for R2? B closer, you are going to get B, C, D anyway you will get, but it is not our relation. So I can say that B determines C is possible. What about C closer? C, D, B. Am I right or not? C, D, B. Means what I can conclude? C determines B is possible. What about 2 level? They are trivial. What about the R3 relation? B closer, you are going to get B, C, from C you can get D. So B determines D is possible. What about D closer? D, B, means that D determines B is possible. So we find all functional dependencies which are possible for individual relations. Now what you have to check? At the end we have to check for whether the actual functional dependencies are preserved over here or not. Is A determines B is there? Yes. B determines C? Yes. Is C determines D? It is not directly available, but it is available indirectly. C determines B, B determines C. According to the definition of functional dependency preserving, closer you have to find, right? So it is preserved. What about D determines B? Yes. So as all are preserved in the subrelations, I can say that option A is the correct answer. Given gives a lossless join and is dependency preserving. It is not called. Okay. Next one. Which one of the following statements is false? Any relation with 2 attributes is in BCNF? It is true statement. So if I say that a relation with two attributes, it is in BCNF. Definitely 100% redundancy free. A relation in which every key has only one attribute is in 2NF. Definitely, right? If an attribute having one attribute, if a candidate key having only one attribute, there is no chance of getting partial functional dependency. So this statement is also true, right? What about this CRD? If you read the C option, a prime attribute can transitively depend on a key in a 3NF relation. Am I right or not? So that is what happening, right? If A determines B, B determines C, A determines C is getting, right? That's the reason we are going for to remove the transitive dependency, right? So there is no problem. What about like option D? A prime attribute can transitively depend on a key in BCNF relation? No, there is no concept of transitive dependency. So this is the false statement. So option D is the